specific, we are talking about physical equilibrium, and we are on positive deviation. Okay, we talked about the routes law, we talked about negative deviation, sketching those curves, the boiling point composition curve, the vapor pressure composition curve, all those curves for both a solution that obeys the Raoult's law and for a solution that deviates negatively from the Raoult's law. The videos are there, they are in our classroom, they are on YouTube. You can go there and watch all of them. But don't forget to subscribe. Don't forget. Just hit the subscription button so that whenever I add a new video and we have studied, you can always go back and check. Okay? Yeah. So now we saw that with negative deviation, just a reminder, if the vapor pressure that is predicted by the Raoult's law, for it negatively deviates. Okay? The pressure doesn't reach that is predicted by the Raoult's law. So it doesn't reach that is predicted by the Raoult's law. It doesn't. So we said with negative deviation, it doesn't reach that predicted by the Raoult's law. And I mean the vapor pressure. So with positive deviation, or before the positive deviation, so if the vapor pressure does not reach that predicted by the Raoult's law, the boiling point therefore is going to be higher than that is predicted by the Raoult's law. So right now you should know the difference between vapor pressure and boiling point, and what boiling point is, what vapor pressure is, and stuff like that. Okay?
Let me see you later. But it's 150. Pause.
Yeah, so guys, with positive deviation, here, the vapor pressure is above that predicted by the Raoult's law. It is simple. The total vapor pressure of the system is higher than that is expected from the Raoult's law. And by now, I think, even if we don't, but anyway, there is, when you are teaching, you don't assume people know. So I will try to go deep to explain to somebody who doesn't know. So the total vapor pressure of the system is higher than that expected by the Raoult's law. So you know the Raoult's law is P, okay, is predicted by the partial vapor pressure of a given component, then times the mole fraction of a given component, and then plus the partial vapor pressure of another component times the mole fraction of that component. Okay? So from this, you predict the vapor pressure, and this is Raoult's law. Now for this one, if you actually determine the vapor pressure experimentally, you find that the vapor pressure that you get is going to be higher than that is predicted by the Raoult's law. So this one therefore gives a positive deviation. Now why does it? Remember our concept. For if you have component A, it will contribute its own vapor pressure, that is if it is unknown. And if component B is also unknown, it will provide its own vapor pressure, that is partial pressure of A and partial pressure of B. Now for component A to contribute the vapor pressure, then it means you have to break the intermolecular forces of attraction between A molecules. The same applies to B. You have to break the intermolecular forces of attraction between B molecules. Now, for the vapor pressure to be higher than that predicted by the Raoult's law, Raoult's law assumes that if you mix these two, then the intermolecular forces of attraction between A-B molecules, the adhesive forces of attraction, they are equal. That is Raoult's law. with these ones, with the cohesive forces. Now, for you to behave positively, then the forces of attraction between the AB molecules, the adhesive force of attraction, must be less than the force of attraction formed between the individual molecules. Okay? So as a result, okay, when you hit them, when you hit this, when you mix the two, since the force of attraction holding these molecules close together are weaker than the individual, they will provide a large vapor above the liquid that is high than when each one here, each is heated alone. So that now the total vapor pressure at any temperature T of the liquid mixture is always going to be high than the individual components. And so it will be higher than that predicted by the Raoult. So this, because of these forces of attraction between molecules of different components than the pure components, for example, bond AA and bond BB are broken on mixing two components, and new bonds are formed, of course. And which new bonds? Between the different components. And so when the new bonds are formed, they are the ones which are now broken to contribute to the vapor pressure. To contribute to the vapor pressure of the mixture, so that now the mixture has a high vapor pressure and the mixture boils at low temperature than that expected by the Raoult law. Properties: there is an increase in volume when the two components are mixed. But remember, the Raoult law assumes the volume remains constant. But here there is an increase in volume because the forces of attraction formed are weak, so molecules become further apart from each other. Hence, the density decreases and the volume increases. Then heat is absorbed. You know, when a bond is formed, heat is given out. But when a bond is broken, heat is absorbed. Okay? So because the bonds broken are stronger than the bonds formed, then you're going to use too much heat and you give out less heat. Hence, the reaction is going to end up becoming exothermic. The adhesive force of attraction are weak because the adhesive force of attraction of different components are weaker than the cohesive forces of attraction. Hence, the component is going to behave positively. So, who is going to deviate positively? So graphically, what we've been saying, we can represent it as this. Whereby, this one is the vapor pressure. So we are plotting the mole fraction of the two components. Where you have A. Now, if this is 0% A or 0 mole fraction of A, it means this one will be pure A. Let me get some kind of permanent pen. So this will be A and this one will be 100% A. This is pure A. Now, if this is 0% B or this is 0 mole fraction B and this is 1, then this one is pure B. Now, if this is the boiling point of pure B and this one is the boiling point of pure A, then as you increase, if this is boiling point of B and B boils at slightly higher temperature than this is the vapor pressure, so B has a higher vapor pressure than pure A, so it means B is volatile and A is non-volatile. So if you increase the percentage, if you increase the mole fraction of A, okay, in this liquid mixture, then the vapor pressure is going to vary like this. And this is what is predicted by the Raoult's law. Okay? By Raoult's law, it is going to vary like this. But when you actually determine the vapor pressure of this system, then the vapor pressure actually is going to vary like this. So this is a positive deviation. Why? Because the vapor pressure is higher than that predicted by the Raoult law. And this one shows the variation of vapor pressure of pure A, and you can see this is what is predicted by the Raoult law, and it deviates positively. The same applies. Now if you are to check the boiling point composition diagram for a system that deviates positively, now it will give a minimum. Whereby, for instance, this is 0% ethanol and 100% water. Okay? You can have a look. For water boils at 100 and ethanol boils at 78.5 degrees Celsius. Now when the two systems are mixed, okay, the two behave negatively. In that, yes, water is going to form hydrogen bonds and ethanol forms hydrogen bonds. But when the two are mixed, the hydrogen bonds that are formed, okay, that are formed between water and ethanol molecules, they are weak compared to the individual forces of attraction between water and ethanol molecules. So as a result, the vapor pressure is going to be high and the boiling point is going to be low. And so you get such a curve. So they can say describe how you can obtain pure, maybe pure ethanol. How are you going to obtain pure ethanol? By fractional distillation. And how are you going to distillate? Which mixture are you going to distillate? This one or this one? Think about it. Are you going to distillate this mixture or this mixture? Now, let's say you have distillated mixture C1. So a mixture with composition 1, if you heat it, it will boil at a temperature, this, okay, this degrees Celsius, which is lower than that of water, but higher than that of ethanol, giving off a vapor composition of this, maybe this is V1, that when you cool down that vapor, you get a liquid mixture with composition C2. Now this liquid mixture has more ethanol and less water. Now when you fractionally distillate, you end up forming pure water as a residue, okay, as a residue, and you get an azeotrope. We can say an azeotrope, depending on your kindergarten, as the distillate. Okay? Now, for pure ethanol, you cannot obtain it. And I repeat, you cannot obtain pure ethanol from this. But if you want pure ethanol, then you have to use a liquid mixture that has slightly above the composition. That is, the composition must be above this. So that when you distillate this, fractional distillation, you get your azeotrope as a distillate and pure ethanol as a residue. So that is the concept of fractional distillation. In case there are questions, it's okay guys, you are free to ask. Then if there are no questions, then we can proceed and talk about immiscible liquids. Now immiscible means not soluble. You cannot mix to form a uniform solution. So two liquids are said to be miscible if the two liquids cannot mix to form a uniform solution. For example, if you mix ethanol and water, the two liquids form a uniform solution. That you cannot tell that ethanol is here and water is here. Okay? They will mix and form a uniform solution or a homogeneous solution, depending. But now, the two liquids, two or three liquids, but usually two, are said to be immiscible if when the two liquids are mixed, then one is going to form its own layer, probably the more dense, and the less dense one is going to form another layer. Okay? Now this, you see that this is a layer of this, of liquid A, and this is a layer of liquid B. If for instance, it is oil, you mix oil and water. For example, you have cooking oil at home. You can try it at home. You can try it and see. The cooking oil, even if you mix the two and you shake like how, if you give them time, they will form two distinct layers, whereby the cooking oil is going to settle on top because it is less dense, and the water is going to settle at the bottom. So these are the two liquids which are said to be immiscible. For example, you have benzene and water, whereby the water is a polar compound, and benzene it's non-polar. So when the two are mixed, then there is no way how they can interact. Now, in a mixture of two immiscible liquids, actually this one is even better, this one is even good. They are totally immiscible. That when you try to distillate them, when you try to heat them, then each liquid exerts its own pressure independent of each other. Totally independent of the other. This one, because the two are immiscible, when you hit this one gives its own and this one also gives its own. So as a result, the two will totally, can I say they obey the routes law? Probably. So the vapor pressure above the liquid is therefore going to be simply the sum of the vapor pressures of the two pure components at that particular temperature. You just add. Why? Because the two are immiscible with each other. So that when a mixture of two immiscible liquids will therefore boil at a temperature that is lower than the normal boiling points of the two liquids. For example, you have a mixture of, this is A and this is B, and the two are immiscible with each other. So when you begin to heat this, okay, then each one will vaporize on its own, independent of the other. You saw that with Raoult's law, so with the other ones, positive and negative deviation, they form forces, they can interact with each other to form some force of attraction. Blah blah. But here there is nothing like interaction. So this one contributes independent of the other, and also this one contributes independent of the other. So that in the end, the partial vapor pressure, okay, with the partial pressure above the two liquids is going to be high at lower temperature. So as a result, this liquid mixture therefore is going to boil at a temperature that is lower than the boiling point of the two liquids. So it's basically as simple as that. So the principle, now this one, it therefore leads to the principle of steam distillation, and you are going to see what steam distillation is, and it's really good as far as separation of liquid mixtures are concerned. Yeah, for example, a mixture of chlorobenzene, it has a boiling point of 131, and water with a boiling point of 100 boils at 90 degrees Celsius. Okay, it is lower, okay, than that. It is lower than the boiling point of that one. Even the mixture of aminobenzene and water, it also boils at a temperature that is lower than the two mixtures. So let's see what steam distillation is. Let's talk about the concept of steam distillation. And it's not that complicated, it's not that big. Steam distillation. Steam distillation. You know what distillation is? You know what steam is. So therefore, you know what steam distillation is? Just think about it. You know what steam is. You know steam? It is vapor, water vapor. Distillation, this separation of liquid mixtures by heating, one evaporates and then you condense and then you cool down. So therefore, you know what steam distillation is. And from here, you can look at my drawing, my diagram. I just took a pic in a setup. So you can see there is this one. Then you have the round bottomed flask. Is this? No, this is. It seems like a volumetric flask, but anyway, it's not. It's not. It is not. Then you have a dye bag condenser, and then where are you going to call it? So therefore, what is steam distillation? It is simple from what you are thinking about steam distillation. It's a technique of separating two immiscible liquids, okay? Or separating two immiscible liquids that must be immiscible with water, okay? At a temperature that is below the boiling point of the two liquids by bubbling steam through it. You have a mixture, okay? You have a mixture of A and B. Now, you want to separate A from B, okay? Now, the two liquids, they must be immiscible with water, all of them. However, one must be volatile than the other. Now, since the two are immiscible with water, then we shall pass their steam, and you know steam, by the way, is hot. Steam is water at 100 degrees Celsius, hotter than the real water. If you want to confirm that, you boil water and then you just open. Fwa. Just open without reasoning. You will confirm that steam is hot. So we shall pass there this steam in a mixture of A and B. Now when we pass their steam, now because the two are immiscible with water, each is the more volatile component is going to vaporize out, okay, together with steam that is passing through the mixture. But because they are immiscible with water, then you can cool down and you get pure B and you get pure water because it is immiscible, or all the two components are immiscible, so there is no way how they can dissolve in water. So you get each component on its own, and then you can separate the water from B, maybe using a separating fan. So you separate two immiscible liquids, or the two liquids that are immiscible with water at a temperature below their boiling point by passing their steam. So that is steam distillation. And it has been used. If you study industrial chemistry or chemical engineering, you will frequently use this. Okay? In purifying organic compounds from their non-volatile inorganic impurities. Inorganic compounds have a high melting and boiling points. And organic compounds are volatile. So to separate them, to get pure organic compounds out of these ones, then you pass their steam, okay, in a mixture or in an impure organic compound. Then the organic compound being volatile, it will vaporize and it moves along with steam. Okay, so if this is your mixture, for instance, you heat steam, this is where you're going to heat steam from, and then you pass this hot steam through your mixture of organic compound. Okay, so that the organic compound being volatile, it will vaporize and continue along with water through the condenser, and then condensed and then collected here together with the water. But because the organic compound is insoluble in water, then the two form two different layers, two distinct layers, whereby water might settle at the bottom and then the organic compound might settle at the on top. Then you just pour everything in the separating funnel, and then you run out a layer of water and you remain with a pure layer of organic compound. Then the non-volatile, the other inorganic compounds, because they are non-volatile, they will remain in this flask. They will remain here as impurities. Okay? And then the water, because being immiscible, they can be separated using a separating fan. So it is basically as simple as that. There is nothing hard here. Okay? There is nothing hard here. So separation of immiscible liquids which have boiling points that differ greatly from each other. That's the importance with this. And the two liquids must be immiscible. We are going to see, okay, the limitations for it to be separated by this, how you should do. So steam is passed over a heated mixture of two immiscible liquids, and then the volatile is first isolated with water as a distillate, and then the non-volatile remains in the distillation flask as a residue, and then, yeah, for example, that one as a residue, and you've separated. So for example, you may have a mixture of 2-nitrophenol and 4-nitrophenol. You can separate them using steam distillation, whereby the 2-nitrophenol is isolated first with water because it has a lower boiling point. It is more volatile than the 4-nitrophenol. You can, by the way, even this one can come in explanation question, that during steam distillation of 2-nitrophenol and 4-nitrophenol, of a mixture of 2-nitrophenol and 4-nitrophenol, 2-nitrophenol is isolated first with water because it has lower boiling point than the 4-nitrophenol. Or even when they don't say that, they can say 2-nitrophenol has lower boiling point than 4-nitrophenol. And then they say explain. Can you explain that? Can you go for it as a chemistry student, or you just count bars of the iron sheets? But whatever it is, then it is what it is. It's okay. So with 2-nitrophenol, let's try to explain. With 2-nitrophenol, this is you have phenol here, okay? You have the OH, and then you have the nitro group here, okay? Now this is 2-nitrophenol. Then with 4-nitrophenol, yeah, we didn't talk about this in organic chemistry, but good, you have a chance to talk about it. Now with 4-nitrophenol, you have the OH here, and the nitro group is on carbon number 4. Now you can see that these groups, this one and this, they are close to each other, okay? But with 4-nitrophenol, these groups, the OH and the nitro group, it is nitro, not amino. Sorry. Maybe let me try to delete. That was. Let me try to delete. It is nitro, not amino. So you have nitro. So that is 4-nitrophenol. And this is, that is 2-nitrophenol. And then this is amino. So this is 4-nitrophenol. Now, the nitro group, here it is on carbon 4 and it is far away from the OH group. You can see that? But with this, the nitro group is close to the OH group. You can also see that. So as a result, with 2-nitrophenol, you're going to form what we call the intramolecular hydrogen bonding or hydrogen bonds. So you're going to form what we call the intramolecular hydrogen bonds. That is within molecules. The molecules, the oxygen here, is going to associate with the hydrogen here. So you form the intramolecular hydrogen bonds. But with this, there is no way how you can form the intramolecular hydrogen bonds because molecules are far away from each other. So by all means, you form the intermolecular hydrogen bonds. Inter, it's between molecules. Intra, it's within a molecule. Now the intramolecular hydrogen bonds, they are weak, so weak. But intermolecular hydrogen bonds, they are too strong to be broken. So that's why this one end up becoming volatile and this one being non-volatile. So because the two have different boiling points and the boiling points are really high, the difference in the boiling points is really high, then they can be separated using steam distillation. Whereby the 2-nitrophenol and water, after forming the distillate, then you can cool down and you form the distillate, and then you separate the two immiscible by using the two immiscible. So use the separating funnel and you run out water and you remain with you remain with 2-nitrophenol. So that's how simple, that's how cool it is. Now you may be wondering that why shouldn't I just use simple distillation? Now remember, you are passing out steam, which is water vapor. Okay? Now by passing out steam, it means the vapor pressure above the liquid is going to be high than when you just distillate. Okay? Yes. So when the vapor pressure is high, then it means our two components will boil at lower boiling points. Now remember, you are isolating organic compounds and stuff like that. Then you prevent these compounds from decomposing and you isolate them out when they are intact. Okay? When they are the way they are. So isolation of organic compounds with higher boiling points when ordinary distillation is carried out. Substance is isolated at lower temperature because the mixture of the substance and steam boils at lower temperature. And then separation of miscible liquids whose components have high boiling points which are not close to each other. And the component with lower boiling point is isolated first with water as a distillate. So then how can we determine the composition of the distillate? Obviously, we know the distillate has water and one of the component, actually the one which is more volatile. Okay? So how then can we determine the composition of the water in the distillate and the composition of the liquid mixture? Sorry, of the component, the volatile component in the distillate. Then we employ this formula. So from that simple formula, guys, you have mass of the substance, and which substance? The volatile one, the one which vaporized and added itself in the vapor or in the distillate, and then plus the mass of water within the distillate. If we take the ratio, okay, of the mass of the substance to the mass of water, that ratio should be equal to the vapor pressure of that substance times the RFM, or the relative molecular mass of the substance, out of the vapor pressure of water times the RFM, or the RMM of water. So if you take the ratio here, it should be equivalent to the ratio there. Okay? So therefore, guys, we can use this to determine anything. I can give you this, I give you this, I give you this, I give you this, I give you this, and say what was the mass of the substance in the distillate. Or I can give you the mass of the substance in the distillate, mass of water in the distillate, vapor pressure of water at that temperature, relative molecular mass of water, which is 18, that one is obvious. Then I give you the vapor pressure, and then I say determine the molecular mass of the substance. So whichever way, you can use this formula wisely, okay, to determine anything, anything, anything. And I guess we have an example here. For example, yes, we have example X, sorry, example 1, and says that compound X is steam distilled at 80 degrees Celsius. This is 80, not 800. So it is steam distilled at 80 degrees Celsius and 760 mmHg. Okay? Now the distillate is found to contain 90% by mass of X. Okay? 90% mass of X. Now the vapor pressure you've given, the vapor pressure of water at this temperature is 240, and the question wants you to calculate the formula, the formula mass of X. You can really do this. This is something cool. This is something simple. You can all do that. Let's see. From our formula, which is the composition, let me use some kind of permanent pen here. So from our formula, which is the mass of the substance, mass of X, okay, out of mass of water in the distillate of water, okay, in the distillate, is equal to the vapor pressure of X times the product of the vapor pressure and the RMM of X out of the vapor pressure of water times the RMM of water. So from this, we know everything. RMM, water. We know everything. What is the mass of X? You have 90% by mass. So it means if X is 90, then the mass of water therefore is 100 minus 90, which is 10. Okay? This is percentage by mass. In case you want, you see, you have 90% of X in the distillate. So if you have 100% of the distillate, and out of 190 is water, so there is X, then what is water? It means water is 100 minus 90, which is 10. So that's why I've said 90 out of 100 should give us what is the vapor pressure of X. Now, you see, the vapor pressure of water is 240 at this temperature. Now for a liquid to boil, the vapor pressure of the mixture must be 760 millimeters of mercury. But at this temperature, you can see.
Excuse me, teacher.
Yes, Innocent.
How did you, pardon for me, how you got to that thing?
How I got the 10. That's good. Yes, I know you. One of you would ask. So you see, I have my distillate. I've corrected my distillate. And if I weigh my distillate, okay, its mass is 100 grams. The total distillate, maybe it is here. Its mass is 100 grams. But they have told me that of 100 grams, 90%, 90 grams, okay, is X. Okay? 90 grams is X. So can't you find the mass of water? Because this distillate, it has X and water. Okay? Our distillate has X and water. So if you have the mass of X, can't you determine the mass of water? And you have the total mass, which is 100. Yes. So if we say 90%, it means of the total, 90 is X and 100 minus 90, it should be 1. So that's how I've gotten the 10 for water. Not so? That's brilliant. So now, the vapor pressure of water at 80 degrees, it is 240. That is vapor pressure of water. Let me first clean here. Yeah, I think the cleaning is okay. Now the vapor pressure of water at 80 degrees Celsius is 240. But still, remember you are passing steam in a mixture containing X and some other thing. But here we just gave you the distillate. We are not interested in the other thing. Now after passing steam in a mixture of X and the other thing, we are forming the distillate. The distillate of X and the steam that we are passing, which is water. But remember, for you to boil, then the vapor pressure above the liquid mixture must be equal to the atmospheric pressure, which is 760 millimeters of mercury. Now, it means if water at this temperature is 240 and the X and the water, they are two immiscible liquids, then it means if I add the vapor pressure of water, which is 240, plus the vapor pressure of X, okay, they should equal to the atmospheric pressure, which is 1 atmosphere, which is 760 millimeters of mercury. Okay? So therefore, the vapor pressure of X is going to be equal to 760, not so, minus 240 millimeters of mercury. So the answer is the vapor pressure. Of X at this temperature. So what is the answer? So this one is going to be 0, and then 6 minus 4, that is 2, and then 5. So 520 millimeters of mercury is going to be the vapor pressure, okay, of our liquid X at that temperature. So therefore you have this, you have this, you have this, you have, can't you get the RMM? You can. So therefore this is going to be 520, okay, times the RMM of X, okay, out of out of what? The vapor pressure of water, which is 240, times the RMM of water. Should I really calculate that? It is 18. Okay, water is here, which is H2O. So it is 1 times 2 plus 16 times 1, which is 18. Meanwhile, you should be calculating this and get me the answer, which is 18. So therefore, our RMM is going to be equal to, if we take 90 times 240, okay, times 18, okay, is equal to this one 520 times 10. So guys, you should get the answer here, times 10. So if you put this on the calculator, you should get the answer, and the answer is, since it's the question just wants formula mass, so it's not relative.
74.7692.
That's brilliant. So it is 74.7, so it is 80.
7692.
Yeah, so 74.8, which is 75. So since the question wants just formula mass, then the answer is going to be in grams. So it is, guys, it's as simple as this. Not so? Yes. Any queries as far as this is concerned? No questions? Okay, if there are no questions, then you try out this. And by the way, for the people who will be watching this video, if I say try out this question, so when you're supposed to pause and then you try out the question, because I usually pause the recording and then I attend to people who are trying out the question. So when you are watching the video, so you should pause and try out the question. Then when you're done, then you continue with the video, because usually the continuation, it is usually the answer to the question, because I usually calculate the question after. So let's all pause and try out the question. Yeah, thanks guys for that. Yeah, I've seen your work. It was good. So now let's do. So now the question says, still let me use some permanent ink. So when Y was steam distilled at 96, so it is at 96 degrees Celsius. Now the vapor pressure of water at that temperature is 730 millimeters of mercury. Okay, now that is the vapor pressure of water at this temperature, and the distillate contains 74% of water. So now mass of water, it is 74%, and then mass of Y is 100 minus 74, which is 20, which is 26. Not so? Now from our formula, which is mass of Y out of mass of water okay, should be equal to vapor pressure of Y times RMM of Y out of vapor pressure of water times the RMM of water. So what is the mass of Y? It is 26. Okay. What is the RMM? Sorry, what is the mass of water? It's 74. What's the vapor pressure? Now, they have told you that at this temperature, the vapor pressure of water is 730. But you know, the vapor pressure of water, okay, of water which is 730, plus the vapor pressure of Y should give us, because it has boiled, it has evaporated, so it should be equivalent to the vapor to atmospheric pressure, which is 760 millimeters of mercury, which is also equal to 1 atmosphere. And so therefore, the Vp of Y is going to be 760 minus 730, which is 30 millimeters of mercury. So therefore, we shall put here 30, okay, and then times, what is the question? The question wants molecular mass, mm, y, divided by 74, which is, no, 730, which is the vapor pressure of water, 730 times the molecular mass of water, which is 18. So if you do this, you will calculate and get the answer. So guys, what's the answer?
The answer was 153.9 grams.
So it is 153 point
9.
.9.
And you're not sharing the screen.
Okay, I'm not sharing the screen, sorry. So, point grams. Since the question just says molecular mass. But if the question says relative, then if you put grams, then you lose it all. Okay? Yes. Yeah, so that's how simple it is. Now you're going to do this. As usual, you're going to pause the video and do this. Okay? And then, but then you won't do it now. I'm going to clip the screen and like I told you, and I send it and you do it. Maybe we shall do it when we come back in our next video. Then let's talk about the principles of steam distillation, and I've already talked about all. There is nothing new here. Number one, the substances to be isolated must be immiscible with water. You know why? So that each exert its own vapor pressure independent of the other, so that the two boil at lower boiling points. Number two, so that the component which is in the distillate can easily be isolated from water by just merely a use of a separating fan. So that's why the two substances must be immiscible with water. Substance to be isolated must have a higher molecular mass, so that a reasonable amount of a substance is obtained in a distillate. Otherwise, if you just use like a substance with just maybe 10, even water has a higher molecular mass than it, then you obtain literally nothing in your distillate. So it should have a high molecular mass. Then the impurities must be non-volatile, so that they do not contribute, or they don't contribute to the distillate, so that the distillate is purely the other volatile component and water. Then finally, the isolated must exert a high vapor pressure near the boiling point of water so that a reasonable vapor pressure, it exerts a reasonable vapor pressure for it to boil at a temperature that is lower than the boiling point of water. Otherwise, if it boils at a temperature higher than the boiling point of water, then you form a distillate that is purely water. You can imagine. You form a distillate that is purely water. So the higher the vapor pressure of the volatile component that is going to be isolated, then the higher is it going to be in the distillate. And so the higher it will be, that the higher that component that will be obtained. So basically that's how cool it is. And I want to stop here for today's lesson because this is another, yes, it is the same, but something new. Okay, so you go and try out the question I've given you, this very question. Try it out where need necessary. You can email me, you can text me via WhatsApp, or you can drop in our classroom. Whichever way, I'll be able to receive your question. Okay? So otherwise, let's have a nice time, guys.